video, we're going to discuss ideas from chapter 12, although it's going to be a little different than what you find in the book. So just focus on the ideas that we're going to discuss in this video, not so much in the book itself. We're going to look at rates of the reaction and what influences those rates. For a reaction to occur, the reactant molecules have to combine with each other to produce a product molecule. To be able to do that, we need two criteria to be fulfilled, and this is summarized in the collision theory. First of all, the reactant molecules have to be able to collide with each other, but not all of those collisions are going to produce products. There are two criteria for the collisions to be successful. One of them is that as the reactant molecules combine or collide with each other, they have to collide in the correct orientation, correct angle, if you will. If they do not have the correct orientation, they will just bounce right off each other and then continue on their merry way without ever reacting together. You have to think about it in terms of, well, we want the reactant molecules to combine with each other, and as they're combining, they are breaking certain bonds and they're forming certain bonds. The bonds that are forming are bonds of product molecules. The bonds that are breaking are molecules of the reactants are breaking bonds, and then they're reforming different bonds to produce product molecules. For that to happen, these molecules of the reactants have to kind of orient themselves in three-dimensional space in such a way to encourage the formation of new bonds. And if they don't do that, then they miss their opportunity. The collision will not be successful. That's the first part. The second criteria is that these molecules have to have enough energy in the form of kinetic energy, so they have to be moving fast enough that when they combine with each other, collide with each other, they overcome that first those repulsive forces, and as they combine with each other, they will overcome those forces and form new bonds. Okay, so there's the two criteria from the collision theory. Well, here's what a progression from reactant to products looks like in terms of energy. So we've got, on the y-axis, we got Gibbs free energy, and in the x-axis, we've got the progression of the reaction. Here's my reactant molecules, and they have a certain amount of energy, and then here's my product molecules. They have a certain amount of energy as well. Now, if the initial energy of my reactant molecules is higher, as you can see, this is higher than my product molecules, then the reaction is going to proceed in the forward direction. So it's going to move from reactants to products without me having to add more energy to it necessarily. Now, as you can see, well, the opposite is true. If the reactants or the products had higher energy than the reactants, it would not be proceeding in the forward reaction from reactant to product as it's written. It would probably proceed in the opposite direction from products to reactants, so in the reverse reaction, just because of the change in energy. If we're looking at this diagram here, I do have my reactant molecules higher in energy than the product molecules. However, this reaction does not proceed directly from, as you can see, doesn't proceed directly from the reactants down to products. We have this little curve here. So the energy of the reactant goes up a little bit, goes over this hump to be able to come down and resolve into products. Well, this energy here, the energy change between the reactants and the top of that hill, is called energy of activation. And on top of that, this C here is called the transition state. So this is the state in which the reactants are breaking their bonds. Those molecules are breaking their bonds and they're in the process of forming product bonds. So different bonds are being formed. So some bonds are being broken and some other bonds are being formed. And so it's a transition state, which is a little higher in energy than the initial molecules that I have, the reactant molecules have. And so you can see that those molecules have to have enough of kinetic energy to be able to go over this hump to proceed then into making products. The energy change between the products and the reactants, so this F here represents that energy change, is negative, which means that the reaction is going to proceed as spontaneous in the forward direction from reactants to products. If it were higher here, I would have a positive energy change, which means it would not be spontaneous in the forward direction, but it would be spontaneous in the opposite or reverse direction. So the activation energy is the minimum energy that is required to break the bonds between the atoms of reactants. So this energy here that's represented by D is the minimum energy that's required to be breaking those bonds between reactants and getting ready to form the new bonds for the products. Now, how do I get to speed up the rate of a reaction? The rate of a reaction is given as the change in concentration over change in time. Now, for the denominator, if the denominator stays the same, the only way I can increase the rate is to change the concentration. So if I increase the concentration without changing the time, if I increase the concentration, the rate of the reaction will increase because I get a larger numerator for the same denominator, which will increase this number here, which makes sense, right? If I am looking at, this is my initial, I have this concentration of the reactants, and if I increase that concentration, I increase the number of molecules. Well, if you think in terms of collision theory, we will have more collisions because we have more molecules, and hopefully more of those collisions will be productive, will be in the correct orientation for them to proceed to products. So if I increase the concentration of my reactants, that is going to speed up the rate of the reaction, how fast the reaction is going to proceed. I can also increase the temperature. Temperature is related to the kinetic energy of those molecules. And so, going back here, if I have a number of reactant molecules, but I increase the temperature, I also increase the kinetic energy of the molecules, or how fast they are moving. And so as they have more energy, they can overcome that. If we go back to, if we go back to here, they can overcome this transition energy of activation here a lot easier because they have more, they're moving faster, so they can get over that hump a little easier. Think about going up a hill. If you're on a bike or a motorcycle, if you go slower, Well, it's going to take you a little bit of time to get over that hump, but if the faster you go, the faster you're going to go up the hill. You're going to overcome that a lot easier, that little hump there. So I can increase the concentration, I can increase the temperature, and that speeds up my reaction rate. There's another way to do that. The last way to increase the rate is by involving a catalyst. The catalyst itself doesn't get involved in the reaction itself. It doesn't get used up. It doesn't get, so it doesn't react at all. But what happens is it alters the speed of the reaction. Typically, it increases it. Catalysts have several characteristics. So let's take a look at them. The first is that they decrease the activation energy of a reaction. This is the first curve that we had, the original curve, where we talked about how the reactants have to get over that energy of activation hump to go down and produce products. So this is the curve without a catalyst. This is the new curve with a catalyst. So if I add a catalyst, note that the only thing that I change about the reaction is that I decrease this D here. I get a new D, which is lower than without the catalyst. So I lower the energy of activation. I don't have to go as high up here, but I do not alter the activation or the energy of the reactants, nor the energy of the products. Those numbers stay the same. The only thing the catalyst does is it lowers this hump. And so it's easier for molecules to go over it. They can go over it without having really high kinetic energy, and so it can speed up the reaction. It can stabilize the transition state. If you think about, well, it takes a little bit of time for these molecules of the reactants to reach that transition state. If the energy of activation is lower, they will, and the catalyst can actually stabilize those bonds as they're breaking and the new bonds as they're forming, then I don't need to spend that much energy to reach that transition state and to proceed to products. And so by stabilizing that transition state, I can make this reaction happen faster. And so that's the second way a catalyst can help speed up a reaction. One is lowering the activation energy. Two is by stabilizing that transition state. As I mentioned earlier, it does not change anything else about the reaction. So the energy of the reactants and the energy of the products stay the same. What happens is you lower that energy of activation value. And lastly, a catalyst is not used up or altered in any way in the reaction. So it doesn't partake per se in the chemical reaction. It's the same as it starts, as the reaction starts, and it's the same as the reaction ends. So it doesn't take part or get used up or get altered in the reaction at all. All it does is it stabilizes that transition state so that the reactants can proceed to products a lot faster by lowering that energy of activation. So remember what a catalyst is and what it does and how it affects just the energy of activation, but it doesn't change the energy of the reactants or products. And that is what we're going to talk about in chapter 12.